In this last video, I want to make the disclaimer that numbers 10 and 11 are legitimately challenging. Way more challenging than you would ever see on a test, a quiz, or even in math analysis. So the reason I'm making that disclaimer is so if you feel as though you're kind of barely hanging on to this idea, that you don't stretch yourself too thin. I don't think questions 10 and 11 are essential. So if you only want to focus on what you really need to be able to do, I would limit your attention to only numbers 8 and 9 and sort of stop there. If you're willing to push yourself a little bit, then bear with me through number 10. But again, I just want to make sure I remind you, this is a really challenging question. And in a similar way, so is number 11. There's nothing wrong with getting overwhelmed with this question and quitting at any point. This is not a question in number 10 that I would ever give you on any sort of assessment, and I wouldn't expect you to be able to do it on your own. So please don't feel like you have to push yourself too far. But that said, I know that some of us are going to be up for the challenge, so I'm going to do question number 10 in the hopes that you can really give yourself that opportunity to soul search a bit. Are you up for the challenge? If so, great. And if not, no judgments. But at least make sure that you're going into this with your eyes wide open, knowing that this is meant to be a hard question and that you at any point can make that judgment call to decide whether you're in over your head or not. Now in question number 10, the first thing I want to do is to think about the situation. You've got a stack of bricks, and it's referring to a different stack of bricks because number 9 was also about a stack of bricks. So it's just meaning as a reflection of that same idea. Each layer contains one more brick than the layer above. The top layer consists of a single brick. If there are 105 bricks in the stack, how many layers are there? So let's think about this stack of bricks. It says the top layer consists of a single brick. So one brick. I'm just going to make a little dash. That means that each layer underneath it contains one more brick than the one above. So the second layer would have 2 bricks. The third layer would have one more, so 3 bricks. The fourth layer would have one more, so 4 bricks. The fifth layer would have 5 bricks, and so on and so forth, until apparently I've used 105 bricks. Now notice that phrasing. That doesn't mean there's 105 rows. It means if you add up all the bricks for however many rows I have 105 total bricks in the entire stack. So that means I don't actually know how far I'm supposed to keep going. How many bricks am I really supposed to keep adding to this stack? How many rows? How many layers? Now the reason why I'm not sure how far to even draw is because right now I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. At the moment I have 15 total bricks. Definitely not even close to 105, but how close? 15 plus 6, and then that plus 7, and that plus 8, and then that plus 9. I guess I could do that for a while until it adds up to 105. And if that's the easiest way for you to answer this question, go for it. But if you want to think about it in terms of a series, so that we can try to use a formula, let's maybe analyze what we know. And I'm going to go back to turning this into a problem like all the other problems that we've been doing with a table of values, so that we can keep this familiar terminology consistent through every problem that we're doing. N should be implied to be like which row we're on. So let's say we're on the first row, N is 1. How many bricks do I have in that row? That's 1 brick. So think of N as the row number, and think of T of N as the number of bricks in that row. So that'll help me kind of break down how this table can look. So in the first row, row 1, I have 1 brick. In the second row, I have 2 bricks. In the third row, I have 3 bricks. In the fourth row, I have 4 bricks. In the fifth row, I have 5 bricks. So I don't know if making this table is very helpful, but it's certainly helping me stand to reason that now I can see some sort of pattern. The number of bricks definitely has a pattern. And I know that if I add 1 plus 2 plus 3 plus 4 plus 5 plus however many rows I'm going to need, it's going to add up to a total of 105 bricks. You can tell I'm focusing on the bottom row here, not the top row of my table, because the bottom row is the number of bricks, and that's what the 105 represents. So I want to kind of stick with what I know. The bottom row seems like it's going to be more useful to me. So let's focus on that bottom row. I'll again just kind of highlight this so I can keep my attention focused on just what I need. And let's think about that pattern. Remember, on this page, the common theme is to ask yourself, is this finite arithmetic, finite geometric, or infinite geometric? Look at it for a second. Is one of those formulas jumping out to you? Now, if you think logically, is this finite or infinite? If you keep adding row after row after row after row, it has the possibility of being infinite, but we are distinctly told that there are 105 bricks in the stack. We're not adding forever. We must have stopped after our bricklayer put down the 105th brick and said, I'm done here. So there must be a finite number of bricks. It's got to be a finite sequence because we stopped after the 105th brick. We stopped there. So I know for sure this is finite. But finite what? Finite arithmetic or finite geometric? Let's look at the pattern. 1, 2, 3, 4, 5, 6, 7. That seems to be adding by 1. So if the adder is 1 every single time, that implies we must be arithmetic. So this must be a finite arithmetic problem. And now I know which formula to use. That's fantastic. I've been using that formula all over the place on this page, so it's nice that we have such consistency. Let's think about our finite arithmetic series then. Our finite arithmetic series formula is 1/2 a sub 1 plus a sub n times a sub n minus a sub 1 all over the adder plus 1. Same formula over and over. The more we write it, the easier it gets to use it. So let's analyze. A sub 1, first term, I have that. A sub n, that's going to be an issue. I don't know what the last term is. The last term isn't 105, that's the total number of terms. I don't know when the last row in my table happened. They didn't actually tell me how many layers I made. In fact, that appears to be the question. How many layers are there? We don't know. We have no idea how many layers there are. We don't know what the last layer was. We don't know where it stopped. We know it stopped, but we don't know where. So that's an unknown value. We've never had to deal with that before. Remember my disclaimer a few minutes ago that this is going to be a tough question? This is why. We've never had to deal with an unknown last term. So let's think about this, and let's think about the math that we might have to do when we have an unknown quantity. Let's first focus on what we do know. We know 1/2. That's good. We know a sub 1. A sub 1 is the first row. There's 1 brick in the first row. But we don't know a sub n, so I'm going to leave it as a sub n. I'm going to leave it as a variable. Now going into the rest of my formula, I still don't know a sub n, so again I'm going to leave it as a variable. Minus, fortunately I do know the first term was 1, over, I do know the adder is 1, plus 1. Now, you might be looking at that saying, okay, Herbert, that's all well and good. How are you supposed to know what a sub n is? And perhaps more importantly, how are we supposed to know what to do with the 105? But let's think about it. Something had to be a sub n. We don't know what it is, but something had to be a sub n. So I had to be able to do 1/2 times 1 plus something, and that same something minus 1 divided by 1 plus 1. And that whole process should have given me an answer of 105. So now the question that comes to mind is, okay, if this is an equation of sorts, can I solve for the part that I need? Can I solve for a sub n? It is a messy looking problem, but I can't type it into my calculator. I don't know a sub n. My calculator doesn't know either. It's not like your calculator can solve for something it doesn't understand. So let's think about turning our algebra brains on for a second. What if this is an equation? What if this is an equation for which a sub n, a variable, needs to be solved for? How could we solve an equation like this? Now, my instinct, first of all, is to get overwhelmed, but I'm going to think for a moment, could I potentially clean up this equation? Is it overwhelming just because it looks weird with all the fractions and stuff? Maybe I can clean it up to make it look a little less weird. 1/2 times 1 plus a sub n times, now let's look at this part, a sub n minus 1 divided by 1. Dividing by 1, do you really need to divide by 1? No. A sub n minus 1 doesn't need that fraction, plus 1. And some of you are looking at the inside of that last parenthesis saying, Herbert, you can clean that up even more. Why are we bothering making this look so complicated? -1 plus 1, those are going to cancel each other out. And that's true. They totally are. So our algebra instincts are strong here. Let's cancel that out. So I have 1/2 1 plus a sub n times a sub n equals 105. Now remember, our goal is to solve algebraically. A sub n is our unknown variable, but if your algebra brain is on now and saying to yourself, a sub n, got to get a sub n by itself, that's a great instinct to tap into. Let's think about how we can do that. If we want to focus on solving for a sub n, anything that's not a sub n we should get rid of. That 1/2 has nothing to do with it. That 1/2 is just multiplying, but it doesn't have any a sub n's attached to it. Let's get rid of it. To get rid of the 1/2, we have two options. You could divide by 1/2. Sometimes that's kind of confusing, divide by a fraction. So you could always multiply by its reciprocal on both sides, because multiplying by the reciprocal will effectively cancel it out of the left-hand side, which is what we wanted. We wanted to get rid of it, and canceling it's a great thing. So now I have 1 plus a sub n times a sub n equals 105 times 2, or 105 times 2 over 1 is 210. Now, this is where the algebra gets tricky. And this is, again, why I made that disclaimer at the beginning of the video. This is not an easy problem, because this is an algebra problem that we have to now think about. I have to get a sub n by itself, but I have two different a sub n's. So I don't know if I want to deal with them separately, because if I want to get it by itself, I feel like I should be dealing with both of them simultaneously. If I separate them, that's not going to do me any good. So what I'm going to do is a step that you might not have necessarily thought of, but bear with me. I'm going to combine these two parentheses together. I'm going to multiply it together to clean it up. 1 times a sub n is a sub n, plus a sub n times a sub n is a sub n squared. And that is where some of us might have just gone off the rails, because we went, what, squared, what? Now, the subscript n is probably a little confusing, so if you want to drop the n and just write it as a plus a squared, that's completely fine, if that helps simplify things. But do you notice the structure here? You have something squared and something that's not squared. And this, again, is where I'm going to make a move that you might not have necessarily thought of yourself, but hopefully you can see why I'm doing it. I'm going to switch the order of things. And again, I'm going to temporarily drop the sub n just so it doesn't look so confusing. I don't want the subscript to confuse our algebra here. So let's focus really quickly, if we can, on just the a. I'll just leave off the sub n for a moment. Does that problem look familiar? Not familiar as in we've done it today, or even in the last couple of weeks, but just in general. Does that look like an algebra problem we've seen before? Because my instinct here is to say, that certainly looks like a diamond problem. It looks like a trinomial. Usually the third term of a trinomial is on the same side, so if I move that term over, a squared plus a, now minus 210, now it really looks like a diamond problem. And again, you can throw these sub n's in there if you want to, but they don't need to be there. What I really want to remind myself is, I can totally solve this for a. It's a diamond problem, and I can do this diamond problem. The diamond problem needs numbers that multiply to negative 210 and add up to 1. Now that's a pretty daunting task. There are actually a lot of numbers that multiply to 210, and I'll save you a little bit of time. I'll give you a slightly more convenient approach. The numbers that actually work are 15 and negative 14. And again, you could make a list of numbers that multiply up to 210 and just kind of guess and check and guess and check and guess and check till you find numbers that work. But I just know, because I happen to have memorized a few times tables, that 15 and 14 happen to be 210. It's just coincidence that I know that, but you can always guess and check a bunch of numbers till you find them yourself. Now let's make sure that we finish factoring them. That means that my factors are a plus 15 and a minus 14 equals 0. That's how a factoring problem would work. But this is equal to 0. I still have to solve it. So I'd get a plus 15 equals 0 as one separate problem to solve, and a minus 14 equals 0 as a separate problem to solve. Remember, that's our zero product property. So I would solve and get a equals negative 15 for one possible answer, and a equals positive 14 for the other possible answer. Now, if you're looking at this going, whoa, 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 what are we solving for? What is this supposed to be? This might be a convenient time to bring back the a sub n. The sub n has really been attached to this a this whole time, and I disregarded it just so it wasn't going to confuse my factoring, but let's bring it back, which you're always allowed to do, and let's look at these answers in context. Which of these answers makes more sense with what we were trying to figure out? Zooming all the way back out so I can put my work back in perspective again, what was a sub n? What did it mean? When I think back all the way to my original setup, a sub n was the last term in the series of bricks. And if I think about the series of bricks, which of these answers makes more sense? Do I really have a row with negative 15 bricks in it? Or do I have a row with 14 bricks in it? Intuitively, 14 is the only number that to me makes sense as a number of bricks. How do I have negative 15 bricks in a row? Was I like digging bricks out? I mean, that doesn't make sense intuitively. So negative 15 must have been some sort of extraneous solution. A solution that comes out when we solve, but in context doesn't make sense as a solution to the problem. So that must mean that a sub n must have been 14. In other words, the last term in the series must have been 14. And to rephrase that in one more way that might make it a bit more clear, that means if I was making my stack of bricks with 1 brick, 2 bricks, 3 bricks, 4 bricks, then I must have had to keep going all the way until the 14th row of bricks. 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14 bricks in that bottom row. And if I added up all of the bricks in the entire picture, I would have added up to exactly 105 bricks. If you don't believe me, try it. Go back to this formula, the formula that we knew we had set up, the formula that we kind of stalled out on because we didn't know what was in the last row. Now we know. The last row has 14 bricks. And I'll plug 14 into that formula so I can verify that this really does work. 14 plugs in as my unknown quantities. And let's do this. 1/2, and I'll get my calculator ready, 1/2 times 1 plus 14 is 15, times 14 minus 1 is 13, divided by 1 is still 13, plus 1 is 14. Yep, 105 bricks, just like we thought. So, the moral of the story is, we now know that there are 14 layers in this little stack. Again, that is a hard problem. That was not easy. To have to know that you had to do algebra, first of all, that was already a bit of a stretch. But then notice the algebra that you had to do. Factoring? That was a real stretch. That brought in some semester 1 stuff in a really unexpected way. So remember at the beginning of this video when I said that this was a hard problem, and that you don't need to be expected to do a problem like it by yourself? This is why. This is a stretch. This is like brilliant mathematician level right here, which, great. If you followed along and you think you can do a problem like this, that's awesome. But if you don't, please don't be hard on yourself. Please don't tell yourself that you need to study this problem over and over again and do 5 more just like it so that you'll be ready for anything. This is not a question that you'll need to know how to do. This is not a question that you're going to be assessed on. This isn't even something that in math analysis or even in calculus we end up needing. So don't worry. This is a flex, if nothing else. This is like the equivalent of doing a handstand. Cool if you can do it. Awesome if it looks very impressive. But at the end of the day, can you live a fully satisfying, fully fulfilled life without ever knowing how to do a handstand? Of course you can. So this is like the handstand of the packet. Cool if you can follow it, cool if you can do it, not necessary for success. So putting that in perspective then, I just want to bear in mind that question number 10 is a total flex, so is question number 11. If you can do it, awesome. If you can't do it, don't worry. But I'm going to challenge you with number 11 if you're up for it. It's like the handstand again. If you're up to trying it, go for it. I mean, what's the worst case scenario? You end up getting a little bit stronger, end up strengthening your muscles? Not the worst case. But that's, again, not necessary. You can be plenty strong in this section without doing number 11, and it wouldn't hold you back at all. Make that judgment call for yourself. But now that you've seen a really hard example, hopefully now you have a good idea of the breadth that this chapter can cover, so that you have a sense now towards the end of the chapter of what we've learned, what seems important, and what seems less important. So now going into the end of this chapter, the review section, you'll have that perspective built in.